And let's go ahead and get into this step 2 question. I will link in the description below where you can get the exact same materials if you don't already have them. So let's go ahead and take a look at the first parts of problem 1. So we have to sketch the graph of this minimum, and then they go ahead and define for us what minimum is when you're looking at two functions. So let's go ahead and just write down. Okay, so we know what this is going to look like, just taking all of the calculus and everything. We've got a lot of experience with these kinds of functions at this point. But I think that from what I can tell in the examiner's report, they really want just a lot of justification and a lot of detail. Like a lot of their critique is just a lack of information on this sketch. So you're not going to want to just do this and say, hey, I'm done. You're not going to get a lot of credit for that. They want to see your justification. And so we want to write this as a piecewise function. And the reason for that is that we have these intervals here where this function is changing. So we know that from negative infinity, that's an 8. From negative infinity to x equals 0, you have 2x, and then x equals 0 to x equals 2, x squared, and then x2 to x equals infinity, back to 2x again. So these are going to be the intervals of the piecewise function here. So I'm going to say from negative infinity to x equals 0, and then give my justification, x equals 0 to x equals 2, justification, and so on. So that's really what we have to do in order to get just a really good score on this part. So we want to go ahead and write down the intervals. And what would you do if you didn't know the intervals, or it's maybe like a more complicated function that you can't really picture? What you should do is just find the zeros for the function. So you have x squared is equal to 2x, subtract it from both sides, 2x, you have 2x, you have x squared minus 2x. So then you just find the roots of this polynomial. So when x is equal to 0 and when x is equal to 2, you're going to have an intersection. And the intersection points are what we are looking at, because that's when our function could change behavior. So we need to investigate. So let's start when x is equal to, when x is between negative infinity and 0. We have to investigate when x exists in 0 to 2, and when x exists to infinity. All right, so this is our piecewise function. So let's have our justification now for why we think that 2x is going to be the minimum for the first one. Okay, so we know, let's just go ahead and write this down, from negative infinity to 0. So I think the best way to prove why 2x is the minimum is to just write down, so x squared is a parabola, so it's greater than 0 for all values of x, greater than or equal to 0 for all values of x. Okay, but then 2x is less than 0 for all x in this interval that we're looking at. So we're just saying, okay, function b 2x, it has values that it's going to take on that are negative in this interval negative infinity to 0. But x squared is going to be positive or equal to 0 no matter what for all x. So that's a good enough justification for this part here to say, okay, therefore y equals 2x is the minimum. So let's go ahead and just write that here. And let's move on to the next interval. So the next interval is going to be 0 to 2. So for this one, I would go ahead and just show that you're thinking about this function. Find the rate of change for the first function when it's equal to 0, and then you find the critical point for that function. So the reason we want to find the critical point is really just to show that we understand what we're doing and we're not just plotting parabolas, because that's going to be part of the justification for why the parabola x squared is the minimum in this range, because its rate of change is 0, and that's right when it intersects with 2x. But if you take the 2x function, then you find that its rate of change is 2 for the entire behavior. So it doesn't have a critical point. So what that means is there's no rate of change for 2x where it's not changing. It's always a positive 2. So that's part of the justification for x squared being the minimum, because if they're equal to each other at 0, so they intersect at 0, and then the rate of change of the x squared is 0 at that point, but the rate of change of 2x is 2, then obviously 2x is going to be increasing at that point. So it's going to become greater and greater as we move from 0 to 2. So that's not going to be the leg that we stand on. We have to say other things, but it's just good to show that you understand what you're doing here if you want to get like full credit. So then what we're going to say then is that we know that when x squared minus 2x, when it's less than or equal to 0, we know that for those values of x squared is the minimum. If we just take the exact same inequality and just subtract 2x from both sides, that's what we get. So for this function, it's the values of x that satisfy this inequality are x that exists between 0 and 2. Because at 0, this is true. We would have 0 is less than or equal to 0. And then as we increase, we have 2. And so we would have 4 minus 4 is less than or equal to 0. So that would also be true. And then in between. So we just need to pick a value. So let's pick let's call this function h of x here. So we need to take a look inside of this interval. That's a quick way to do it. So h of 1, we'll say, is 1 squared minus 2 times 1, which is equal to -1, which is less than or equal to 0. So then if we just pick a value in between 0 and 2, we find that x squared is in fact less than 2x, because x squared minus 2x is less than or equal to 0. There is, I would also go ahead and say that h is continuous, and that is a good thing to state, because we know that if we're talking about if we're talking about just this interval here, for a function that is not continuous, it is not enough to it's not enough to just say for any function that you're going to have this smooth behavior. And the smooth behavior is what is guaranteeing that this x squared part is in fact the minimum for all values of x in between 0 and 2. Right? Because if I had a function that was not continuous, and many functions are not continuous, if it wasn't continuous, then there's totally a chance that I could have just some weird random value here. And, I don't know, just a hole. So it is important to just mention h is continuous, because that in the math world is sort of saying, look, I understand that the reason that I can sort of do a hand wavy thing and generalize is because this is continuous. Like if this was not continuous, I would have to be using some kind of theorem, like the intermediate value theorem. But we don't have that much time, obviously, on the exam. But it's really easy to just say h is continuous. And I think that you're more likely to get better scores if you can just show that you're thinking. All right, so yeah. So let's see. So what we show here then is that that x squared is the minimum in this interval. So we just have one more interval to check, and that's for x in 2 to infinity. And my screen is kind of messing up on me. Okay, so for x in the interval from 2 to infinity, what's our justification going to be here? So we're going to go ahead and we're going to assume that x squared is greater than 2x, because we're just going to claim that 2x is the minimum for this interval. So we're going to back up that claim. We're going to need to just do the same thing and show that x between 2 and infinity, that this statement must be true. All right, so yeah, what we know is that that these two functions intersect when x is equal to 0 and 2. Well, in this case, when x is equal to 2, we can show that that 2x is the minimum if we can show that the rate of change of x squared is greater than the rate of change of 2x. So that would be a good place to start for this one. So we know that the rate of change of x squared is 2x. We know the rate of change of 2x is 2. And so we know that 2x is less, 2x is greater than 2 when x is greater than 1. So what that tells us is that the rate of change of x squared is greater than the rate of change of 2x when x is greater than 1. So what that is telling the examiners is that we know that we're right here. We know that we're looking at x equal to 2. Oops. And we know that we just showed that the rate of change of x squared is actually equal to the rate of change of 2x at this point. And so they're on an even playing ground. Their values in the range are equal at this point, and they're increasing at the same rate. But when x is greater than 1, then x squared starts to have a greater rate of change. And that's going to continue, right? Because the rate of change of 2x is 2 for all x. It's just going to stay constant. But the rate of change of x squared is going to continue to increase at a rate of 2x for all x. So that is our justification. And what we have written here is the justification for that. So that would be probably good enough. Let's see. So 2x is greater than 2 when x is greater than 1. I'd probably say something like since x squared is equal to 2x at x equals 2, and the rate of change is greater for all x greater than 1. You could just say x squared. Just say 2x equals the minimum. So something like that, just to justify. And now we'll just go ahead and do the sketch, which we know. Sketch is the easy part. And you are allowed to bring a ruler, which is nice. So, and I think, again, like, it takes time, but not that much time, and you'll probably get a much higher score if you spend a little bit of time just making sure that the slope looks right. There are some comments in the examiner's report just saying, like, some points weren't very clear. So I would definitely like label it. Okay, and I would go ahead and also just really quickly just show that the rate of change of x squared is equal to 0 at this point. That's what this is. We've just written that, and we're sort of showing them that we know. So rate of change is 0, and then it slowly starts to pick up. Something like that. That's good. Okay. And then we know that our intersection with the 2x line is going to occur right here. Good enough. Okay. So, yep, just go ahead and label all of these. And that should give you full credit, I think, for this part.